Hello students. So in the last video lecture we studied the free vibration of a spring mass system. So a spring mass system or undamped system. So there was no damper there. Okay. Free vibration meaning that we had no force applied. Once you gave disturbance, after that you release the force, basically let it vibrate by itself. So we saw that if there is a spring with a stiffness K and mass M which is attached at the end, if you give slight disturbance, this will keep on oscillating. The oscillation will be something like x naught sine omega n t, where omega n is the natural frequency. This is how the motion of the mass attached to a spring you can describe it. So free vibration means we are not applying a force all the time. Means at t equal to 0 you have applied, that's it. After that there is no force applied. So because of that initial disturbance, the motion will start and it will be sustained. Okay, now it has only a spring and mass system only. There is no damper there. So it's undamped system. You call it undamped system. Okay. So today we are going to study free vibration of a damped system. Okay. So that is today. So vibration of a damped system. Okay. So what is the meaning of that? The meaning of that, we are also going to add something here. We are going to add a damper. Okay. So damper. So like this. So we will have a mass which is attached to a spring and also attached to a damper. So the system is like this. So see, like this one. Okay. So we have a spring mass damper system. And damping basically is little bit there in all materials. So few materials have a lot of damping, few materials that have negligible, but still some amount of damping will be there. Okay. So here we are, this one is a viscous damper. So we call it viscous damper. Okay. When you say viscous damper, that really means it has a property, and property is if you have a damper like this and if you apply a force like this one, then there is a relationship between how this point is moving. Let us say you are fixing this point and you are applying a force at the other point. If the damping coefficient is C, then relation between this force applied F and the velocity here, not velocity but displacement, okay, is given by F equal to Cx dot. So x dot is velocity. So this is how the relationship is the model of a viscous damper. So the same damper we are going to apply here. So meaning that we have now three things here. A spring, for a spring, what's the law? For the spring, if you apply a force here, and if the displacement is x, so relationship is F equal to k times x, where k is the spring constant or the stiffness of the spring, and then there is a mass attached to this one. Okay, now before we actually know details about it, we have to know what is the equation that governs this spring mass damper system. Okay, so once we know the equation, again like the last video lecture, here also the equation will be some differential equation that we need to solve and see how the solution look like. So looking at it, if we have to find out what is the differential equation, we have to again draw here the free body diagram. So let us say it's vibrating. Okay, so you have given some disturbance and you keep on start vibrating, it's vibrating. So at one instant of time, this mass is somewhere here. Okay, and let us say if this is my point of reference, so from here to here it has moved from the this is the mean position. Okay, this is the equilibrium position where you have given disturbance. After that, this has started vibrating. Distance from here to here is x. Okay, so velocity is x. Displacement is x. Velocity will be x dot, like that. So if you want to find out the equation of what the equation it governs, then we have to draw a free body diagram. So at that position, if this is M, now it has moved from here to here. So a spring will be in tension, and hence there will be one force which is upward, which will be equal to kx. The other force which will be because of this, and we know that if the velocity is x dot, then the force which is applied is cx dot. Okay, so in here, if the velocity of this one is x dot, there will be a force which will be opposing to this one. So the cx dot, which will be okay. So if the velocity of this going down is x dot, and damper is going to resist it. Okay. So if you are pulling the force, if the pulling the mass this way, damper will try to resist it. Okay. So the force which will be applied because of a damper will be opposite to that. So if its velocity is this way, the force will be that way, and that's why it is balancing here. See, since the force is this way, cx dot is backward, hence it is balancing. So similar thing you can apply here. So like the spring opposes the displacement, the damper will oppose the velocity. So if velocity is this direction, cx dot, or the force, resistance force because of the damper will be in the opposite directions, hence the direction of that will be this. So total force will be equal to cx dot plus kx, and you know that from the Newton's second law of motion, that is has to be equal to mx double dot. But remember, one mistake we did here is we have to add minus here because both of them are in opposite direction. Our x is this direction. Okay, so forces are negative. So minus cx dot plus kx equal to this, and hence from here what do we get? We get we get mx double dot plus cx dot plus kx equal to 0. So this is the equation it is going to follow. Whenever, again, this is a second order ordinary differential equation, and we have to solve it. And with all differential equation, there has to be some boundary conditions, right? So, but in this case, since this is an initial value problem, right? So we have to know the initial condition. So what is the initial condition? So initial conditions are, okay, so initial conditions, we have x is 0. At x equal to 0, we have to know what is the value of at x equal to 0. Okay. Then at x dot equal to 0, what is the value? So those the value we have to know, then only we are going to solve it correctly. If you don't have these values, then we will not able to do it. Okay. So far, what do we have? We have mx double dot plus cx dot plus kx equal to 0. Okay. So let's find out the solution, general solution for this one. We forget about the initial conditions right now. Okay. So depending on the initial condition, we put there and we go from there. So we will derive the general solution for this one. Again, you must have done already this kind of equations, differential equation you must have solved. Okay, but like you had differential equations mathematics course, there I'm sure this kind of second order differential equation should have been solved there. Okay, but still we are going to repeat it. In general, the solution of this kind of equation is typically x equal to e to the power s t, okay, where s is some constant, okay, where s is a constant, okay. So x equal to est, okay. Now we put this value there and we see this is the general solution. Okay, so here there will be also a value. Let's put a like this. Okay, so if that is the case, then we go there. So we put the value here. So m, then x double dot. So what you get? A s square, then e s t, okay, then plus c s e s t plus k, again here a we have to write here, a plus k, then a e s t, that is equal to 0. So there is a mistake here, so I should be m here multiplied by this one. There is no line. Okay. So what we see is in this case a and a e to power st, a e to power st, a e to power st. So all common. So what we have finally left is ms square plus cs plus k is equal to 0. Okay. So this equation, using this equation, we find out the value of s. And what is the value of s? So s equal to, we will use like minus d plus minus root b square minus 4a c over 2a. Okay, okay. So where b is equal to, in this case Okay, not to be confused between this C and this. This is I'm writing for reference, as you for quadratic equation we know that from our high school. So this is what we get from here is S equal to this one is minus C plus minus root C square minus 4 times M times K divided by 2A, so 2M. So this is how what we get. Yeah. So or S equal to, here we write minus C over 2M plus minus root and we take this inside, so this becomes C square over 4M square minus 4MK over 4M square. Okay, so is equal to minus C over 2M plus minus root. Okay, here we will do further simplification. So 4M square minus, here what we see is K over M. Okay, so K over M, now we will write like this one. Okay? So omega n will define, okay, we'll define omega n, which is the natural frequency. Omega n is equal to root K over M, so that we know, so we'll write down here. Okay, and then we will also define one thing. Here the ratio of C, we call it zeta, and that will be C equal to C over 2 root Km. We will call it xi. Okay, so then this value C over 2M, so C over 2M will be equal to C, then multiplied by K, and then 2MK. Okay, then fine, then we have K, so we have 2 C 4MK times we have 2K here like this. Okay, so okay, so we don't have to do like this one. So here instead of having K, we can have root K here. So root K, okay, multiplied in the numerator denominator both. So what we get is C over 2 root M or root Km, so root Km, and then here we have root K over M. Okay, so what do we get? This term is what we call xi, and this one is omega n. So we get omega n. So this value will be equal to xi times omega n. Hence, this value is xi square omega n square, and this is omega n square. So what we get is s equal to minus xi omega n plus minus root under, and here we have xi square omega n square minus omega n square. Okay. Omega n, as you see, is a common, so we can say s equal to omega n, and then we have minus xi plus minus root and xi square minus 1. Okay. Okay. Sorry, it's a zeta. Okay, it's not xi, it's zeta. So omega n minus zeta plus minus root zeta square minus 1. Okay, so this is what the S looks like. Okay, so depending on the value of xi, we will see whether S is a complex number or it's a real number. Okay, so there are three conditions. One condition will be conditions. We write is conditions. Okay, so conditions. Number one, condition one is what is called critically damped. So this is critically damped. Okay, when it happens when zeta is equal to 1. Okay, now number two, you call it overdamped. Overdamped, and that happens when zeta is greater than 1. Okay, so in that case, if that is the case, you get two unequal roots, right? So and here three but real roots in this case. The third case is we call underdamped. So underdamped. Okay, and this is when xi less than 1. Okay, so what when zeta is less than 1, what you see here, this term is a imaginary terms, because this is less than 1 minus 1, this becomes a negative number. Square root of that we get I, so that means imaginary terms comes into picture, and since the solution is e to power st, so what we get here is imaginary term. In this case means we get e to power I term somewhere. So e to power I in this case times t times some constant, that really means it is a sinusoidal term. Okay, so we will now see what is the meaning of this. Depending on this condition, the solution will be different. So we are going to compare them. Okay. So far what we know is there is equation mx double dot plus kx, we write like cx dot first, cx dot plus kx equal to 0, and the solution is x equal to e to power st, okay, where s equal to omega n, and then we have zeta, okay, then plus minus root under zeta square minus 1. So this is the solution where omega n equal to root k over m and zeta is equal to c over root k m. Okay. So far we have this. Now we will look at that closely. Okay. Now, let's look at the underdamped condition. Okay, underdamped condition. Okay. Underdamped means xi is less than, zeta. Okay. Zeta is less than 1. If that is the case, then what happens? Then x is equal to, what we get is, in that case, s will be equal to omega n, and then we have zeta, then plus minus I root 1 minus zeta square. Okay, since zeta is less than 1, then this will be real number, so we have here imaginary number here. So what we get, therefore solution will be x equal to, this solution is a like this one. Okay, the solution will be a constant here, and there are two solutions. Okay, so there are two solutions, there are two roots, hence s1 and 2. So we have s1 and 2 is like this one. Okay, and hence x will be a combination, means you will have a e to the power omega n zeta plus minus I root 1 minus zeta square. We will write plus first in this case, and then there will be another term which will have negative part here. So plus 1, it will be a combination of that, and hence we will have omega n zeta minus I root 1 minus zeta, like this. So combination of the two, here we have plus, here we have minus. Okay, so what is the meaning of that? Okay, so let's expand it further. So what we get is a e to the power omega n, also we have to multiply by t, so we have est, so we have s1 here, s2 here, so multiplied by t, so we get omega n zeta t multiplied by ei, this iota 1 minus zeta square, okay, omega n t, so omega n is multiplied here also, okay, plus second term b e to the power omega n zeta t multiplied by e I, we write it omega n multiplied by, here it will be minus, because here in this case is minus, hence we will have minus here, minus 1 minus zeta square here multiplied by t. So we can write it further, and what we get the solution in this case, x will be, one thing will be common, e omega n, then zeta t, okay, and then we will have multiplied by, we have common a, so we have a e to the power I root 1 minus zeta square omega n t plus b e to the power minus I root 1 minus zeta omega n t, like this. Okay, so we get x times this. So this is a here one thing, the solution will be, in this case, will be minus here. So minus b, so we have minus term here. So the value should here be minus here. So you have to go back, okay, put minus, okay, so minus term, all these things, okay. It's important that minus is here. It's actually originally minus, so I just missed it. So minus zeta, so minus e to the power minus omega n times zeta times t multiplied by this. Okay. This term is the exponential term. Okay, so what we see here, if we expand it further, we get e minus omega n zeta t multiplied by, here I term, let's call from here to here term as omega d. So we call it omega d. Omega d is equal to 1 minus zeta square omega n. Okay. So what we get, x, we are going to assume that one. So what we get, x equal to e to the power minus omega n zeta t multiplied by, we have a e to the power I omega dt plus b e to the power minus I omega dt. Okay. We expand it further, and what do you get? You get e minus omega n zeta t multiplied by, expand this one now. So we have a cos omega dt plus a I a sine omega dt. Okay, now b, then we get cos omega dt minus I b sine omega dt. Okay, this is how the solution will look like. Okay. Okay, so we have the solution here. So let's write, we simplify this one further. So we can write x equal to e to the power minus omega n zeta t, and then we have a plus b cos omega d term here. So we can write it as a plus b cos omega dt, okay, and then plus, and here we have ia minus ib, okay, and here we have sine omega d theta. Okay, since this is general solution, we can write this is also as omega n zeta t multiplied by this, let's call it c. So we call it c cos omega dt plus this we call d. So d, and this becomes sine omega dt, like this one. Yeah. So general solution, we are just writing the general solution. So this we can go further and we can write it as something like x, okay, x e to the power minus omega n zeta t, and then here we write it as sine omega dt plus phi. We can also write it like that. So x equal to big X, let's call it X naught, okay, so that there is no confusion. Okay, x equal to x naught e to the power minus omega n, then zeta t. So, and then this, we combine them into sine omega d t plus phi. That we have done many times, you must have done in your other courses, right? So what is the meaning of that? This you can do because you will take this c divided by root under c square plus, so where we can write where x naught equal to root under c square plus d square, we can write, and this is how it is. So automatically, if c over root under c square plus d square, this you are assuming it as, so we can also write tan phi equal to is equal to this will be sine, so this becomes c over d. Okay, so if you use this transformation from here, you will get that. Okay, so the idea is to get this equation we were looking for. Okay. So what you see in the general solution, you have one amplitude multiplied by one exponentially decreasing term, okay, the decreases with time, and the second term is sinusoidal term. So because of that, there will be, if you look at the solution, the output, you will see the effect because of these two, basically. So let's delete this part. So let us say if you want to plot this one with t, so this part will be something like with time, you will have at t equal to 0, you will have value equal to 1, and then this will decrease, and at t equal to infinity it will be 0. So this is how it will be. Yeah. So this is e to the power minus omega n zeta t term. This is sinusoidal term. Okay. So this is sinusoidal term. So this one you can plot like this one. Now this is multiplied with sinusoidal term. So this term is going to sine, if you want to plot it here, this will look like this. So you have the sine, but there is a phi at t equal to 0. There is a phi term, so this will be like this. From here, they will go like this one, right? So something like this one, let us say, and it will keep it constant. Yeah. So amplitude like this one. Okay. So this is sine term. So this is sine omega d t term plus phi term. Okay. With t. Now what we are going to do? We are going to multiply whom? This multiplied by that. Okay, and we want to see how it looks like. And if it multiply by both of them, so how will it look like? This will look like this. So you have this time, and one term will be like this one. The first term, it will look like this one. Okay, so this term is nothing but this term is nothing but e to the power minus omega n zeta t term. Okay, and then on top of that, this is sinusoidal term. So this will be going like this, and so on. Okay. And this is sine term. Okay, so this one is sine omega d This one is total multiplication basically. So this is x x naught e to the power minus omega n zeta t multiplied by sine omega d t plus phi. So this is x equal to this. This is how it will look like. So it will changing, it will follow the exponential decay, right? This is going down like this one. So this represents the undamped, underdamped oscillation. Okay, now let's look at the other two conditions. So we have seen the underdamped. Okay, let's go to critically damped. So in this case, what do we have? The solution is x, as we said, solution we assumed x equal e to the power st, where s we have equal to minus zeta plus minus root zeta square minus 1. Okay, so this and whole thing multiplied by omega n. So this is what the equation we got. So as I said earlier, critically damped means zeta equal to 1, and hence what we get is a solution x which will be equal to, will be of the form of, we have a e to the power minus zeta omega n t. Okay. So we already know how it looks like. Basically, the plot will be, the plot of this will be, so we have x like this one, sorry, it goes t like this one, t like this, and then we have x here. So depending on the initial value, if you want to plot this one, so if the initial value is important here, the initial value is this one, for example, this will simply, it will be going like this. Yeah, so from some initial value x0, and this will decay, okay, along the time. So this is how it will look like. Okay, now third case, we call it overdamped. Okay, so in this case, again the same solution. Here the solution, we have the same one, however we have zeta which is greater than 1, and in this case what we get? We get S1 equal to minus zeta plus root zeta square minus 1 omega n, and S2 is equal to minus zeta minus root zeta square minus 1 omega n. So what we get here, there are two roots basically, and they are not equal. Hence the solution in that case will be a combination of the two. So we will have a e to the power minus zeta, so we write like this, minus zeta plus root zeta square minus 1 omega n t, plus we have b e minus zeta minus root zeta square minus 1 multiplied by omega n t. So we have to take the combination of the two, And if you take the combination, then that may not look like this. That may, depending on the initial conditions, what we will get is something like this. So we will have so yeah. So this may be something like this. So basically there will be a combination of two. So here also we see basically one part is minus zeta omega nt. So one will be visible, which will be something like this, and the other term. So this term. So what I meant is we can write x as x equal to e to the power minus zeta omega nt and multiplied by a, then e to the power zeta square minus 1 omega nt plus b e to the power minus root zeta square minus 1 omega nt. Okay, so this will make the envelope the way it made in the case of underdamped condition. So this one will appear again. This is minus zeta omega nt. Okay, and this one, whatever value we are getting, this is going to scale it. So this will be within this. So you have this and then multiplied by this one. So we get an envelope which is by this one, and this one, depending on what is the initial condition, it will be varying something like this. Okay. We can also plot it. So basically we will do in details when you go to the control theories. Okay, so there we are going to plot it more and we see. Okay, so here it is just the general solution we are interested in. So these plots and all are approximate. Okay, so this gives some idea how the solution will look like. Okay. Someone may ask that why in this case it starts at some value and then keep on decreasing, but in this case it goes up and then decreases. So for that you can see this has two terms. So one, since zeta is more than 1, so this is a positive real number, and this is minus of a positive number, then omega n is also positive number. So what you say, this term increases, say exponentially increases with time, and this term exponentially decreases with time. So the combination of the two, you will see initially this will dominate, this will try to increase the value, right? But what happens, there is this term as well, so that will makes these limited basically. So initially you will see this term, because of this term this will increase, okay, but because of this term this will decrease. Okay, so hence you get increasing first and decreasing. You can plot yourself, you can see how it looks like. And here, because this has just decreasing term only, and hence this is decreasing like this. Okay. Now, having said that this is the general trend, the exact solution will also depend on the initial condition, as I said. So for example, if the initial condition here is depending on the initial condition, this may also go up and come down, or if it is like this one may go down like this and go down like this also. So this all depends on the initial condition. So initial condition is important. Okay, so here what we have derived is just general solution, but we have not actually put the initial conditions. Okay, so in order to know the exact nature of the solution V, you must apply the initial conditions, and then only you will get the true picture. So here all the curves that we have drawn here is just to see the trend, general trend, how it will look like. Okay, so in order to know the exact solution, you have to apply the initial condition. Okay.